Hello, everyone, and thank you for joining us for today's e-showcase, PFAS, an overview and end-to-end treatment solutions. I would like to thank today's sponsor, Veolia. And without further ado, I'm going to hand the presentation off to our presenters.
Thank you very much, Regina. I'd like to thank WEF for hosting this webinar, as well as the broad group of people involved in PFAS, including municipal and industrial clients, consulting engineers, industry partners, suppliers, and vendors, as well as all of you attendees today. My name is Marty Scanlon. I'm Market Development Manager for Veolia Water Technologies and Solutions. I have 25 years of experience in the water industry in design, marketing, and technical sales, and I'm a registered professional engineer in the state of California. I'll be acting as moderator today, so please add your questions to the chat to all panelists, and we'll get to as many as we can. We've got a lot of information to go through today. And it's my pleasure to introduce John Peichel, who will be doing the presentation. John is the global market developer at Veolia Water Technologies and Solutions. He's located in Minnetonka, Minnesota. John's got over 30 years in industrial water treatment using membranes. During his career, he's worked in engineering, sales, and product development. Currently, John's responsible for research and development of new markets involving advanced filtration and separation technologies and related products. John has been focused specifically in the PFAS market for the last 4 years. And so John will be doing the presentation. I'll be acting as the moderator. And again, please add your questions to chat to all panelists, and we're going to try and get to as many as we can at the end of the presentation. First off, I just need to make a quick disclaimer. Specifically, PFAS is a very fast-moving, dynamic topic. And so we have a standard disclaimer that there are so many aspects to what we're presenting, and this is our understanding of the topic at this time. Again, it's a very dynamic topic, and things will continue to change from this point forward.
Thank you, Marty. So welcome, and so glad to be with you today. I'm going to try and cover in 30 minutes to 35 minutes the overview of PFAS, which I will be brief because there is a lot of information out there. I'm going to focus on the scope of the PFAS problem and spend the majority of our time talking about our solutions and experience, and then hopefully leave 5 to 10 minutes at the end for your questions. And as Marty said, put those into the chat to the panelists, and we'll try to get to as many as we can. So if we look at the challenge of PFAS in water, wastewater, and solids, there are 3 key challenges that come to mind. There is the drinking water regulations, which are proposed, particularly in the US, but also around the world. And those proposed regulations can require PFAS treatment to very low concentrations. In addition, we recognize that wastewater often impacts many of our drinking water sources. And so treating wastewater for PFAS, whether you're coming from an industrial facility or even a municipal wastewater facility where you're treating and discharging water containing high levels of PFAS, if that's going to a water body that serves as the drinking water source for someone else, PFAS treatment may indeed be required. And lastly, there is the topic of disposal of PFAS, whether it's captured on a treatment media, whether it's contained in a liquid stream, or it's concentrated to a very high concentration volume that needs to be disposed of. There's various options for on-site and off-site disposal, and we'll talk about those briefly, but that is of paramount concern when people get about tackling the PFAS treatment problem. So I'm now going to turn off my video just to save in bandwidth and make it a little bit easier for the website hosting. So we'll start with talking about regulations, and it's not hard to see PFAS in the headlines on an almost daily basis now. And some of the more recent headlines I've posted here are dealing with bans relative to the dealing with disposal of things like biosolids coming from drinking water and wastewater treatment plants that contain PFAS. We have the EPA in the US issuing guidance on reducing PFAS as part of our NPDES permits. And we have the EPA starting to finalize rules around including PFAS in something called the Toxics Release Inventory. That TRI data basically removes a exemption for low levels of PFAS, requiring industry like manufacturing and power generation, chemical manufacturing, to now start measuring and tracking what the amount of PFAS and the types of PFAS that are being discharged to the environment. All of these regulations are having an impact on us as water treatment professionals, as operators of plants, to keep them in mind when it comes to addressing the challenge of PFAS. So let's just briefly talk about the scope of the PFAS problem. And I'm going to try not to be redundant here, but PFAS, we're learning, it's used in a lot of products, consumer products, industrial products, and firefighting foams. So we can find PFAS just about everywhere because of its different types being used in many, many different applications. When we think of PFAS, we think of it as just one of a family of all the different things that are contaminants of emerging concern, which we include things like pesticides and nanomaterials and microplastics and pharmaceuticals, things that we've grown accustomed to using in society that end up getting into our water and wastewater. Well, PFAS is just one of the pieces of that contaminants emerging concerns, and that's what we're here to talk about today. So what is PFAS? So it's a family of chemicals, and it stands for per and polyfluoroalkyl substances. And within that, there's various types of PFAS, quite a few. Some people estimate over 5,000 individual types of PFAS. And many of those PFAS comes from common consumer product uses that I just mentioned. One of the predominant uses of PFAS is in firefighting foams. Because of their chemical and temperature resistance, they're very effective at dousing high temperature fires. And why are PFAS so resilient? It's all based on this chloride fluorine carbon bond. That carbon fluorine bond basically makes it a strong chemistry bond that's resistant to chemical and heat attack. And if you look at the periodic table of elements, you can see they're both small elements. And as you move from left and up to top of the periodic table, those ionization bonds become so strong. In the lower left-hand corner of this slide, I've listed some of the most common types of PFAS. And we often will generically group types of PFAS into sulfonic acids or sulfonates or their carboxylic acid groups. Those attention to the type of PFAS and structure can give us insights into how to go best about treating them. So if we look at the water cycle and the connection that our industry and our environment has to both water and wastewater, we can see PFAS shows up in a number of different ways and where and how we could be treating. So sometimes we are talking specifically about the treatment of PFAS in drinking water. And other times we're talking about it in the treatment of wastewater because we recognize that that wastewater can get into the drinking water. Or we might be dealing with a discharge of a landfill leachate, which has PFAS, and that also could make its way into the environment and could contaminate our drinking water supplies. So we're going to talk specifically today about PFAS in drinking and wastewater, but recognize that there's a lot of other areas of PFAS treatment and disposal that come into this discussion. If we look at some common types of PFAS, this list identifies the PFAS by its long chemical name, but also shorthand. Shorthand is very common in the PFAS market for people to be specific about which type of PFAS they're talking about. And if you wanted to be even more specific, you could refer to its CAS number, its chemical abstract shorthand number. And that generally leads us into the structure of PFAS, which we can summarize by the number of carbons and the number of fluorines in the PFAS molecule, and go a step further by counting them up and identifying its molecular weight. And that molecular weight and that structure can give us a tip as to when we're analyzing a source of PFAS or a water stream to be treated with PFAS, what's the best treatment way to go about it based on how big it is. So why is PFAS a concern? Because of that resistance to heat and breakdown, it has an impact of surviving in the environment and now is detected in a lot of drinking water supplies. On the right, we have a heat map of just the US, but these heat maps are available in Europe, in Australia. As more and more testing is done on PFAS, more and more people can recognize where the high levels of PFAS are and where they're connected up to, whether it was industrial activity or fighting activity or just consumer goods. What is contributing to that level of PFAS? And of course, why do we treat anything? gets down to its health concerns, that PFAS compounds are believed to be accumulated in the human body. That has come as a result of testing and measuring things like blood serum. And certain types of PFAS have been linked to negative health effects through medical studies and analyzed by the EPA. So that's where the regulations are coming from. And if you look at the regulations in water and soil and solids and waste, this is something that is happening throughout the world and has been evolving over time. So this is a chart that basically tracks some of the water evolution in the US and Europe and Canada, but also is starting to bring in soil and biosolids, and they're recognizing that you can't necessarily dispose of those materials the way we've become accustomed, because the PFAS in those materials can make their way into water supplies. And then there's when we collect these materials or we have waste coming from different industrial applications, the need to dispose of PFAS containing materials properly. So all of these things are continuing to evolve and continuing to make it necessary to take action. If we look at drinking water, wastewater, and waste, they have different aspects to them when it comes to regulation. In drinking water, the EPA in the US has proposed drinking water standards around 6 types of PFAS, and is currently going through kind of final review of consumer feedback or feedback from the marketplace, with a final rule anticipated to be adopted early next year. And if that becomes adopted, then in 3 years, drinking water facilities will have to comply with the proposed maximum contaminant level for these 6 types of PFAS, 2 of which are specific levels. The other 4 are actually used to calculate a hazard index. And if the hazard index exceeds 1, then treatment or monitoring is required. Wastewater has no specific regulations in place today, but EPA is actively working on a new method of analysis called 1633 that will be appropriate for measuring non-potable water and solids in the identification of treatment needs in wastewater. And then there's a lot of regulation and discussion around waste. And does PFAS or specific types of PFAS become listed as part of the CERCLA, the Comprehensive Environmental Response Compensation Liability Act? That basically starts to make the treatment and the generation and the management of PFAS as a hazardous substance much more like we manage other hazardous substances. So today that's not in effect, but we see a lot of discussion happening going in that direction. Here is a slide that details out that hazard index calculation that is part of the 4 types of PFAS in the proposed EPA maximum contaminant level. And you can see that they're using a denominator to weigh the level of PFAS against its suspected, health effects or seriousness of being in drinking water. If we look across the US, we see many states have moved in advance of EPA drinking water regulations and instituted their own limits on drinking water. And they're very specific to a PFAS type, and they exist in areas where this particular type of PFAS is there and recognize that treatment is required for drinking water to protect the public. In Canada, we also see both PFOA and PFAS, the 2 most common types of PFAS, having an enforceable maximum contaminant level. And so it's not as specific as some of the actions in the US, but it also is showing that there is movement towards drinking water regulations around the world. So one of the things that's going on in the US right now is something called UCMR 5. UCMR 5 stands for the 5th Unregulated Contaminant Monitoring Rule, in which the EPA identifies 30 contaminants to test for over 3 years from drinking water supplies that are serving a population of 3,300 members or more. And in that, of the 30 chemical contaminants, 29 are types of PFAS. So where UCMR 3, which was done several years ago, was testing for 6 types of PFAS, we're now getting very detailed data on 29 types of PFAS in drinking water. And that will go into future EPA discussion and decision about additional drinking water limits. So now let's transition to talking about some of the solutions, and we'll share with you some of our experience in treatment of PFAS. We think of PFAS treatment as involving 6 specific steps featuring an end-to-end treatment solution. We have found it is so important that you start with good sampling and testing methodologies to accurately characterize both the concentration and the type of PFAS. And that information can lead to treatability studies and pilot studies that help us get the information for the best design. And during design, we can weigh pros and cons of different technology, the cost to install, the cost to operate. And then when we get into the construction and operation, that's about actually putting into effect that treatment solution. And then at the end, we will always have waste containing PFAS that has to be dealt with and properly disposed of. And so depending on the design and the treatment solution, that treatment can be beneficially done different ways, and we can help work through those options. So let's start with thinking about sampling and testing. Because PFAS testing requires some unique capability and equipment, labs across the world have installed equipment and developed processes, often following standard methods. In our business, we have our Tomball Technology Center, which does water and wastewater sampling and analysis, and we've standardized on testing using EPA method 533, which tests for 25 types of PFAS. And so we get these samples in, we run that in, we give the results to customers who are evaluating technologies, optimizing their treatment solutions. I will say, though, we are not a certified lab, so we are not doing UCMR 5 municipal drinking water testing. We've chosen that approach because we need the flexibility to support a variety of customers from drinking water to wastewater. This is a list of some of the common EPA testing methods. 537 and 533 are the most common ones you'll see, and you can see that they came out at different dates and they have different numbers of types of PFAS, and they're primarily used in drinking water. Proposed method 1633 is in draft, and it's going to test for 40 types of PFAS. And the benefit of this method is it can be used not just for drinking water, but wastewater, surface water, soil, solids, biosolids. And so it is expected to be the preferred standard of testing for PFAS going forward once it's adopted. So this is just a little bit more detail about our PFAS analytical testing capability, method 533. It's in Tomball, Texas, just outside of Houston. We use it for supporting treatability studies, pilot commissioning, optimizing the operation of systems, and really evaluating some of the new technologies that are being developed by a whole variety of companies in the area of PFAS absorption, on-site PFAS disposal, better ways to segregate bulk PFAS from the treatment stream. So all of these things need analysis as part of the evaluation. And then when you put it into actual application, you need to test for PFAS to see how effective it's being and to predict when to change out things like carbon and ion exchange media. Treatability study, this refers to what you can do in the lab as you evaluate a specific stream to be treated for PFAS. You can take a sample into the lab and using methods like RSSCT, rapid small scale column testing, you can get an idea of how one particular material, carbon versus ion exchange, or two different types of carbon, or if you're interested in evaluating some of the new novel adsorbents, these lab testing can give a side-by-side comparison of the effectiveness and the capacity of those materials in collecting and removing the specific types of PFAS that we're treating for. So this could be a first step after analysis before one designs a field pilot or a full-scale system. If pilot studying is desirable, either because the municipal regulation in your state requires proof of the treatment technology, or you want to get a better handle on the cost associated with the life of the media being used, or the effectiveness of a membrane in removing the targeted PFAS that you're trying to remove, a pilot study can be a very effective way to evaluate side by side a desired treatment solution before designing and implementing the full-scale treatment. We have trailer-mounted equipment featured here that often is used in pilot studies because it does allow you to very quickly start gaining data on site and getting faster to designing the full-scale stream and getting a good, accurate prediction of what the life cycle cost of that treatment solution could look like. This is a table that kind of bucketizes some of the various things I've been referring to. And we kind of think about them in two broad categories. Those technologies which separate and those technologies which dispose or degrade PFAS. And there is a whole host of technologies that are standardly used in water and wastewater treatment, like carbon and ion exchange and reverse osmosis. And there's technologies that are maybe newer being developed specifically to address the PFAS problem, particularly like technologies in the advanced oxidation processes, where you're using strategies of electrochemical oxidation, chemical oxidation, plasma, things to dispose of PFAS on site. So you get it all the way to a mineral composition and is no longer PFAS. So many of these things are at various stages of technology development and commercialization, but it's worth keeping an eye on as we try to design both the current and maybe the future most effective treatment solution. If we talk about some of the things that are most commonly used in PFAS treatment today, we would start with adsorption. And the two most common materials used in PFAS adsorption are activated carbon and ion exchange resins. And these materials are very commonly used in water treatment, so they're very well understood. And the suppliers of these medias have optimized and selected different formats that are very effective at PFAS. And we'll talk about some of the comparison between the types of carbon and ion exchange. We have come up with our own treatment approach called LEAP-FAS, which is based on a proprietary design vessel that is useful for achieving ultra low levels of PFAS in the effluent on a consistent and reliable basis. So there's a picture in the lower right-hand corner of a 2-vessel LEAP-FAS solution that we would use for water and or wastewater treatment. And those vessels could be loaded with carbon or ion exchange or a novel adsorbent and give us an ability to treat and remove and put new media in and still maintain ultra low levels of PFAS if that's the treatment goal. So let's talk about ion exchange resin. This is one of the solutions. We can use it in LEAP-FAS, but it is a very effective mode at which you capture PFAS, particularly the variety of PFAS, both long and short chain. In membrane filtration, this is a separation technology, and we use a couple of different types of membrane in PFAS treatment. One of them is our hollow fiber membrane, which is very useful in removing suspended solids, organics, and TOC, which can then be used to pre-treat carbon or ion exchange adsorption, or it can be used as very effective pre-treatment for a membrane system containing nanofiltration or reverse osmosis membrane. And we have a variety of platform membrane technologies. ProFlex and Sirian are two of them, and they are pre-designed skid-mounted packages pictured here that can very quickly be deployed to the field for treating of water. We compare these technologies side by side from the activated carbon, which is the most common form of PFAS treatment today. It is very effective on long chain PFAS. It does require a little longer empty bed contact time, which increases the size of the vessel and the amount of carbon to treat a given flow rate than, say, ion exchange, which is typically a smaller footprint than activated carbon. And they use resins that are specifically engineered for PFAS capture, and they're very good at removing long and short chain PFAS. But they do require low ion content, particularly the anions, and they do require low TOC and organic levels that would interfere with the capacity of the resin. So that's one way that we have found is to pre-filter with ultrafiltration membrane, carbon and ion exchange to make those medias last longer and hold more PFAS. Longer time between changeouts means a lower overall cost of operation. And then nanofiltration reverse osmosis are very effective to a wide variety of PFAS that typically are higher in CapEx and OpEx than activated carbon ion exchange. But sometimes, that is required because there's other things in the water that are effectively removed by reverse osmosis, as well as the PFAS. And so it can be a desired outcome of treating with membranes. Negative on RO and NF is treatment of the concentrate stream. Now you have a smaller volume, but higher concentrations of PFAS to work with, and that has to be taken into account in the overall treatment scheme. And then the last row is really around alternative treatment methods being developed, whether they be novel adsorbents, which would work very much like activated carbon and ion exchange, or some of the more advanced ways of disposing of PFAS or separating them, such as chemical water oxidation or foam fractionation. Some of those technologies are starting to get, tested, piloted, and start to become a full-scale treatment solutions in PFAS. So this is a flow sheet that kind of illustrates the connection between pre-filtration on both drinking water and wastewater, where removal of suspended solids and organics or even heavy metals can benefit the downstream adsorption or membrane separation step. And in many cases, with the very low level of treatment PFAS levels required or being asked for, it's required to treat adsorption and or membrane filtration in 2 steps. You have primary collection followed by a polishing step. So that might result in, say, 2 activated carbon vessels or 3 activated carbon vessels in series, or following a nanofiltration membrane system with a polishing activated carbon or ion exchange on the permeate to meet the effluent treatment requirements. And then in the case of using a membrane for separation of PFAS, we would have to deal with the treatment and disposal of the concentrate, which is commonly approached now with adsorbing with activated carbon ion exchange as a place to capture the PFAS. Now that discharge stream might not have as low a level of treatment of PFAS as required as, say, the drinking water requirement, but it does allow you to meet, say, an MPDS permit for discharging the concentrated salts coming from a membrane system to the environment. This is a slide that talks about hollow fiber membranes, which we have found to be a very effective tool in the treatment of both drinking water and wastewater, because it can be used as an immersed membrane and handle high solids and other materials in the water. It's an excellent pre-filtration to downstream membranes and adsorption technologies. And then we have hollow fiber pressurized membranes, which can be used on smaller plants where you don't have the space or want to have the space of a tank that would hold the immersed membranes. Both styles of UF membranes are very effective in pre-filtration of PFAS separation and capture technologies. If we kind of look at microfiltration to RO, microfiltration and UF, removal of PFAS themselves, not so much. The pore size is large enough and PFAS molecules are small enough that they'll generally pass through, and we get very little, if any, reduction in PFAS levels through those membranes. But when you get to nanofiltration reverse osmosis, the pore size is now small enough, and the charge characteristics of NF and RO membrane do contribute to higher removal rates of PFAS. And we'll share some data that illustrates how nanofiltration and RO membranes compare on specific types of PFAS. We did a test in our lab where we took a source of well water containing PFAS. We did not add any additional, so we didn't spike it. We tested on industry standard 2540 spirals, and we used 3 membrane types: a standard brackish water RO membrane, a low energy RO membrane, and a nanofiltration membrane. And we ran those in batch where we concentrated the feed up to 90% recovery, effectively concentrating salts and PFAS to about 10x their feed concentration. And then we did a calculation of percent removal. And if we look at this data, this summarizes the types of PFAS that were in that well water and what their concentrations were in the feed. And if I draw your attention to the bottom of the feed column, we had about 410 parts per trillion of total PFAS. And if we look at the permeate from each type of membrane, the RO in the first column, we had no detectable measurable levels of those types of PFAS in the permeate. On the low energy membrane, we had a couple of types of PFAS that were measurable, very low still, but now we're starting to see that a more open, low energy RO membrane actually will show if the concentration of the feed is high enough and you run to a high enough recovery, you can detect levels of PFAS in the permeate. And then nanofiltration just shows a much higher level, and we start to see the smaller chain PFAS are the ones that come through, not surprising, and the larger PFAS is removed and rejected. And so we got some percentages there where, all of the PFAS being removed by the RO membrane was below the detection level for our PFAS analysis. We had about 99.1% on lower energy RO and 89% on the nanofiltration. So it gives you a good idea of membranes are right in the size of PFAS that we're trying to filter out and remove. So you have to be selective of what type of membrane one would use if that's going to be one of the technologies to use in the treatment process. So one thing that is emerging as a value is combining membranes with adsorption, where membranes are less sensitive to the chain length and they maximize the removal of short chain PFAS. If that's one of your treatment goals, the membranes provide a kind of a filtration barrier from the feed stream to the treated water, which can be very important for many drinking water supplies, particularly if they're dealing with a lot of contaminants of emerging concern. We can use this approach of treating with membranes to future-proof the plant for other contaminants that may come up in the future, either through regulation or as part of the source water. And that we find that if we reduce the volume in the concentrate and increase the concentration of PFAS, that does help with some of the adsorption technologies and getting more loading of PFAS per cubic foot of media, which can give us a favorable outcome in terms of the overall cost of running media on the concentrate stream as the way to collect and capture the PFAS. I would be remiss on a PFAS presentation if I didn't talk about the treatment technology landscape. Now, we talked about things that are very mature in their stage of development, like RO and activated carbon and ion exchange, and they're very much used in the PFAS treatment. But there is a whole host of other separation and disposal technologies that are at various stages of development, and we just want to raise people's awareness to that those technologies can serve a very useful purpose in the overall treatment scope, and we would be happy to work with you to explore those technologies as some of them come into commercialization. One of the last steps and one of the things that we talk about a lot with customers is what do you do with the PFAS that's captured on, say, carbon or an exchange resin or a novel adsorbent? Well, one of the things to do is to have an EPA-approved disposal facility, which Veolia has one in Port Arthur, Texas, that is basically dealing with the treatment of hazardous waste. And even though PFAS is not listed as a hazardous substance at present, this can be a very effective way to dispose of PFAS in a proper way to minimize or avoid the risk of exposure to the environment. In our overview of a flow sheet option, I talked about the impact of prefiltration, the use of membrane as a separation. There's also this advantage of doing bulk separation on the membrane concentrate. And then depending on where your site is and what the wastewater discharge requirements are or your disposal options, incorporating some of these new technologies into on-site disposal on just the bulk separated PFAS. The water stream that contains all the salts rejected by the membrane would then come through bulk separation and may require some polishing to remove any of the PFAS that doesn't get removed in bulk separation to be suitable for wastewater discharge. And you can see in building this treatment stream how you may start out with prefiltration and membrane separation, and you could add optional polishing either on the treated stream or on the waste stream as regulation and requirements evolved, or as our understanding of the types of PFAS and how they need to be removed evolves. You could add this stuff to a treatment process as those things evolve in the future. So that concludes our walkthrough from sampling and testing to lab treatability studies to field pilot design using carbon, ion exchange membranes, new and upcoming technologies, and then finally the treatment of the final waste containing the PFAS. So if this is something that you're going on, we would encourage and recommend a holistic approach to thinking about these 6 steps when it comes to treating PFAS. And just some 4 takeaways as my last talking point is the PFAS environment just continues to evolve very rapidly. We can expect drinking water regulations will drive what we need to do on treating our wastewater, both from municipal and industrial plants, and that we need to, and stewards of those plants and those water and wastewater systems, proactively consider how we deal with PFAS. Based on where you're located, different states, different countries are going to have drinking and wastewater regulations that may not require PFAS treatment today, but may require treatment in the future. And that on the 3rd bullet, evaluation of risk is up to each facility to evaluate what's your water source. Is it under the influence of an activity like a fire event where they used firefighting foam to put out the fire and that discharged PFAS to the environment? And if that is a risk for your facility, maybe testing and monitoring of PFAS is a necessary step to evaluate your overall risk of future treatment requirements. And today we are very fortunate that activated carbon, ion exchange, membranes are useful in treating PFAS. If you have those technologies in existing operations, but maybe they weren't put in specifically for PFAS, maybe evaluating how those operations are affecting PFAS that might be in your source water or wastewater. And then think about terms of treatment, media replacement, PFAS accumulation and breakthrough, concentrate PFAS levels might be all worth evaluating as part of your evaluation of risk of the operation of your facility. And I think if we know the risk and we collect the right data, we understand the various treatment alternatives, we can be prepared and even be proactive in meeting the needs of PFAS treatment going forward. So thank you so much for your time and attention. And we'll take any questions we can from the chat. I'll bring Marty back in as the moderator and look forward to seeing you in the future.
Great. Thank you, John. I've got a number of questions in the chat.
Okay.
And I would encourage anyone else who wants to add some questions to it. We're probably going to more than use up the time right now. What I would say is if we don't get to all the questions, we'll take a look at them after and try to respond to everyone as we can. But to start off, one of the things with regards to PFAS is the testing. And so one of the questions was, how often, let me make sure I get to it. How often do you test the sampling equipment for residual PFAS or to make sure they are in fact still PFAS free? And is the sampling equipment then kept in a clean room? So it's 4 parts per trillion, or the parts per trillion is some pretty low numbers. And just curious how we address that.
Okay, so a typical sampling kit from our lab and other labs doing PFAS analysis is a cooler. And that cooler is, the purpose is to contain ice to keep the samples cool in transport so they're stable before they get to the lab. In that cooler are the sample bottles of the right material, and along with either prepared sample bottles or a reagent you put in the sample bottles when you take the sample. That cooler typically ships out, sealed with tape, and it does not have to be stored in any sort of refrigeration or clean room. And you could accumulate a number of sample coolers. And when it's time to go and sample, you would go and pull your samples, and you might pull anywhere from 3 to 8 samples, depending on if you're testing different points in the treatment process. And you would typically, sample, every 2 or 3 weeks. And by sampling at different locations, like in a treatment vessel, you would sample at some intermediate sample points in the bed. So you get an early determination of when the bed is starting to exhaust and break through and require immediate treatment. It takes about 3 weeks now to get a PFAS analysis back from the lab. So it's not something where you can test every day, nor would you want to given the expense. But generally, I find customers, when they're starting up and they're getting comfortable with how long their carbon ion exchange is going to run or how their membranes are performing, they will sample about every 3 or 4 weeks. And then as time goes on, they can increase the time between sampling, because PFAS performance doesn't change. It follows its historical pattern pretty well. As long as the concentration and flow rate stays relatively constant, you can expect very similar PFAS removal performance. Thank you.
Thanks, John. Next, I heard the testing of PFAS is complicated because it's easy to contaminate the sample. And given that constant testing is needed, are there automatic systems that can sample to eliminate the burden by technicians?
So it is a concern that when someone, takes a sample, we always, all the labs do a sample blank where you fill a source of DI water that's shipped with the sample kit. So you can test that blank against the other samples and evaluate for field and lab contamination. It is not as sensitive as people think. If you follow the protocols, most technicians are very good at taking a non-contaminated sample. What you see is with the very low levels of reporting available to labs, certain materials like PFBA is a 4 carbon chain PFAS. it's in a lot of the reagents and water supplies that labs are using. And so you'll see some contamination come from the lab background, and it's easy to factor that out from the testing of the blank. But field contamination, in general, I don't see a lot of problem with technicians and people in the field following the instructions and getting a very representative PFAS sample.
Great. Got another one. How long do you typically run a pilot for on-site PFAS performance testing?
So one thing I mentioned is that there is a time between sampling the PFAS and getting the result from the lab, running about 3 weeks. And so in general, you want to run long enough to load up the carbon and the ion exchange and get some idea of how the capacity of that media will work on that actual PFAS treatment stream. And so at least 2 to 3 months of pilot testing is needed to get that data, sometimes ranging as long as 5 to 6 months. And I know that some states actually require you to test a treatment solution for drinking water for at least a year to prove the treatment technology. And in PFAS, that would be ideal. But I think at least 3 to 6 months is the minimum for pilot testing on PFAS treatment.
Okay, got quite a few here. Let me. Are you seeing specific contact time requirements when using granular activated carbon or ion exchange? High flow requirements?
Yes. So empty bed contact time, meaning the time that the water needs to reside in the media, is about 15 minutes. So you take your volume of flow rate and you have to calculate how much cubic feet of media you need to get 15 minutes. Ion exchange is typically less than that. It can be in around the 5 to 7 minute range. So the vessels are smaller, the amount of media is less. And so those are generally good starting rules of thumb, is 15 minutes in activated carbon and say 5 to 7 minutes on ion exchange.
Thank you. Are there situations where both granular activated carbon and ion exchange can be used to treat the same wastewater stream for PFAS?
Absolutely. That's often referred to as a hybrid treatment solution, where you would have activated carbon in the first vessel and you'd have ion exchange in the second vessel. And the idea there is that activated carbon will capture, the long chain. It'll remove TOC, which is impactful to the ion exchange capacity of PFAS. And the ion exchange will then be also much more available and effective at removing the shorter chain PFAS. And because it's, lower empty bed contact time, it's a smaller vessel, so it's not quite as big as the activated carbon. And in some cases where the nature of the types and concentrations of PFAS on the stream to be treated and the treatment goals require both long and short chain PFAS removal, carbon and ion exchange can be the effective hybrid solution to the problem.
Excellent. Let's see, we're running just pretty tight here. When would I consider pretreatment, or what is the value of pretreatment for treating PFAS in my wastewater?
Particularly in wastewater, we see elevated levels of organics, TOC, BOD, and suspended solids. And by having very fine filtration, which ultrafiltration membrane will deliver, you end up extending the life between changeouts of your carbon and your ion exchange medias before you have to change those medias out, or in some case offsite or onsite regenerate them, in meeting the treatment goals that you have for your PFAS. In wastewater particularly, we've successfully employed ultrafiltration as a great way to lower the cost associated with carbon and ion exchange in the removal or treatment of PFAS on wastewater.
Great. I think we're coming up on time. We've got a lot of other questions that are in here. Regina, do we have time for any more, or should we?
You can certainly answer as many as you'd like.
Let's go a couple more questions, Marty, and then we really appreciate this. I mean, I'm watching the questions scroll through the chat, and Marty's got his hands full. But we will try to respond to you individually with answers to your questions as we can over the next few days.
Here's a one on the economics. Are there rough rules of thumb on approximate range of unit capital costs to remove PFAS from, say, drinking water and wastewater? It's quite a
Oh boy.
handful.
Yeah, I'm not so sure that I could throw out a number. Um, there is so much into it. The concentration, the flow rate, the type of PFAS, and what the treatment goal is. Are you trying to get to very low levels so people don't have to report to their constituents or their customers? Are they trying to meet a state requirement of only a few types of PFAS, in which case you might be able to run the carbon a lot longer than you would on a treatment goal that required you to move both short and long chain type of PFAS to much lower levels? So we will end up with capital impacts of single, double, or three vessels in series. And then lowering the empty bed or increasing the empty bed contact, meaning lowering the flow rate, will extend the time between change out. And if you're very remote, you may want to do that just to reduce the cost of labor. So all of those variables make it really hard to peg a number, but those are hopefully some ideas of the factors that influence capital and operating cost.
Okay, we'll take one more and then we'll respect everybody's time and go ahead and end the webinar. But is regeneration of saturated granular activated carbon media or ion exchange resin really an option? Or do industries generally prefer single-use media or resin?
Yeah, it's like any treatment technology. There's pros and cons. There's trade-offs. There is an ability to take ion exchange and activated carbon. There are technologies and facilities that can take and effectively recharge or regenerate those materials, and you can put it back into a less sensitive, or if it's a wastewater stream, the same application for capturing more PFAS. Capacity gets affected. Your regenerated media is not as great as brand new media, but it is a way of reusing the same material, particularly as the cost of materials increases. So it is an option out there, but it is an option that is limited to a very few, applications. And of course, their location has to be very close relative to that regeneration recharge facility. But it is out there.
Excellent. All right. Well, thank you, John. Really appreciate the presentation and the audience. Just tremendous amount of questions. I apologize. We're not getting to them all. They're continuing to come in, but we will go ahead and review them afterwards, and we should have emails, and we'll try and get back to as many of you as we can. But just wanted to say thank you again for attending. And John, any words in conclusion?
No, just thanks for your time and attention and everything you're doing as we collectively as an industry, learn more and more about effectively treating PFAS. So thank you.
Thanks very much.